Welcome back to AP Chemistry. It's Miss Gray, and you're with Falcon High School. So we're at podcast 9.4 now. We're dealing with osmosis and colloids. So let's wrap up our unit about colligative properties by talking about osmosis. Osmosis basically deals with the movement of a substance. To move the substance, we need a semi-permeable membrane. So that basically means we're going to allow some molecules to pass through a network of tiny pores or holes, right? And the substance moves across a membrane from an area of high concentration to an area of low concentration. But when we talk about osmosis in AP Chemistry, we're looking at what's the solvent doing. So if our concentration for the solution is high, then the concentration of the solvent is relatively low. So for osmosis, the solvent molecules are going to go in the opposite direction from what you would normally think. So they move towards the solution that has the highest solute concentration. So the solvent is going from low to high. Just the opposite of what you would normally think, right? So osmotic pressure, then, is the pressure that's required to stop the flow of osmosis. To keep the solvent where we want it to be, then we would need to apply some pressure. And guess what? We use Pivnert to describe that pressure, only osmotic pressure has the symbol pi instead of p. So just like the ideal gas law, the osmotic pressure is going to have to be equalized with atmospheric pressure so that we can measure it. So here's an example of how that might be done. Suppose that we have a salt solution and we use a semi-permeable membrane so that our solvent can flow through, our solvent being water, right? So then as this achieves equilibrium, the water is going to flow into this tube because inside here the water concentration is slightly less than outside the tube. So as soon as the water flows in there, we're going to have some pressure pushing back, and that has to be equal to the pressure of the atmosphere pushing down. Now our examples here have nothing to do with osmotic pressure. They're more examples about freezing point and boiling point. So how do we get molar weights, molar masses for our solutes when we're giving a freezing point change or a boiling point change? Alright, so grab your calculator and let's do some math. Here we go. We have a solution with an electrolyte that dissociates into 4 particles. So I is equal to 4. And it's dissolved in 1200 grams of water, and it now boils at 107.44 as opposed to the normal 100 degrees. So our change in boiling point was 7.44 degrees Celsius, right? And we want to determine the molecular weight. So the first thing I need to do is figure out how to get to moles. If I'm going to do that, I need to get to molality, right? So we take our change in the boiling point divided by the boiling point constant for water, 0.51, and the Van 't Hoff factor, which in this case is 4. So let's figure out what is our molality here. Our change in boiling point divided by 0.51 times a Van 't Hoff factor of 4, and that gives us a molality equal to 3.647. 3.647. Yep, can't write and talk at the same time. There we go. And that's molal. Yeah, there we go. That's a 3, by the way, y'all. 3.647 molal. So what does this mean? This means I have 3.647 moles of my solute for every 1 kilogram of solvent. But do I have 1 kilogram of solvent? No, I have 1.2 kilograms though. So let's set up a proportion. How many moles are in 1.2 kilograms? Do y'all see where I got that? Just move this decimal over 3 times so you can change grams to kilograms, and then we'll get the number of moles for our solute. So I had 4.38 approximately, 4.38 moles. Now don't round in your calculator. It's okay to write down a rounded figure, but don't round in your calculator till the end. So if I have this many moles and I want to find the molar mass, then what I need is grams per mole. So how many grams of solute did I have? Here it tells us right here, 365.3 grams divided by the number of moles, 4.38 moles. And that gives me a molar mass of 83.47 grams per mole. Well, that wasn't too bad, right? Is it getting easier yet? I sure hope so. We're going to keep on practicing this until we get it right. We don't practice until we can get it right. We practice until we can't get it wrong. So now let's do another one. The mass of aluminum perchlorate that must be dissolved in 3.53 kilograms of water to give a solution with a freezing point of negative 13.33. Well, that sounds like a big change, but look at our Van 't Hoff factor. I'm going to get aluminum and 3 perchlorate ions. So I have a Van 't Hoff factor of 4. That's pretty significant. What's our change in freezing point? Remember, water freezes at 0, so our change in freezing point was 13.33 degrees Celsius, lowered by that much. And then Van 't Hoff factor is 4, and K for water, for the freezing point anyway, is 1.86. And molality, that's what we're going to have to find out. So our molality is going to be the change in my freezing point divided by freezing point constant times Van 't Hoff factor. So we take 13.33 divided by 1.86 times 4, and I have a molality there of 1.792 molal. And that means 1.792 moles of our solute for every 1 kilogram of solvent. All right, but I don't think we have a kilogram of solvent, do we? That's never given so easily. We have 3.53, so how many moles then will there be in 3.53 kilograms of our solvent? I get my number of moles to be 6.32 moles. Great, so now we have to find what mass. Oh dear, what mass? Before we had to find the molar mass, and now I'm asked to find what mass? No big deal. We know how to change mass to molar mass and moles to grams and all that good stuff. So let's start with what we know, 6.32 moles. And how do we change moles to grams? For every 1 mole, how many grams? Use the molar mass. So we have aluminum perchlorate. So 1 aluminum and 3 perchlorate ions, that's going to give us a molar mass of, let's see, 325.3 grams. So we take our moles times molar mass, and I get 2,057.58 grams of this aluminum perchlorate. It seems like a lot, but that's about 2 kilograms, and we have 3.5 kilograms of water, so it's a reasonable amount. Always ask yourself whether or not your answer seems reasonable. So if you put your answer in kilograms, that's fine. I'm going to leave mine in grams because it doesn't specify one way or the other. And you probably noticed by now I'm not paying much attention to sig figs because in these problems with freezing point depression and boiling point depression, our sig figs sometimes limit the accuracy of our answer. So, you know, we'll pay attention to sig figs some other day because I know you know how to do them. All right, well, let's go on back to colloids. Colloids are basically the dividing line between solutions and heterogeneous mixtures because we can almost identify the particles. They're also known as colloidal dispersions, and basically this is like a solution made up of a really big particle. The particle size is basically what determines whether something's a colloid or a solution. And generally, a colloidal particle would be clusters of atoms that stick together, or ions and molecules that stick together in clumps, or maybe even just a single giant molecule that forms a colloid. So we'll look at a representation here. A true solution has particle sizes that are smaller than 10 to the minus 7 centimeters. That would be about 100 nanometers. But then when the particle size gets bigger, into the range of micrometers, then that would be a colloidal solution. And suspensions is when we have particle sizes that are greater than that. So it's not truly a solution at all. And this is what causes a colloid to have a cloudy appearance, because you can almost see the particles. You just can't distinguish them from the solvent. And one way that we can find them is by using the Tyndall effect. In the Tyndall effect, when you shine a light through a solution, it would pass straight through. But in a colloid, it gets deflected. It bounces off the particles in the solution, and it looks sort of foggy. Let me show you what I mean. So here's a solution where the light passes straight through, but in this colloid, you can see the light gets scattered, and you can see clearly the path that the light's taking through that solution because the colloid bounces the light around inside there. There's a couple different types of colloids. The hydrophilic, of course, would be those that like water, and hydrophobic are those that can't stand water. They stay away from it. So colloidal particles have to be removed from our wastewater, and one of the processes we use there is coagulation. Coagulation basically means that we're going to add some strong electrolytes to grab those particles and pull them out of the solution. One commonly used electrolyte is aluminum sulfate. It's called alum. And alum, basically aluminum sulfate, is used so that we can pull large particles, Al3, there we go, Al2SO43. We can pull a lot of the charged particles that are in the wastewater into large clumps so we can filter them out. So in wastewater treatment, this process, coagulation and flocculation, occur when the pH is adjusted using calcium carbonate a lot of times, and then also alum to pull all the large particles into big clumps so we can filter out and remove from the wastewater. And that's it, really. That's all that we needed to do for Unit 9. We have finished colligative properties, and so you know what that means. We're going to have a test. Yay! See you soon.